Hello everyone, my name is Luis Kutz, and I'm the professor of the module Waste and Combined Heat and Power, CHP. I'm so glad that you are going to be joining us in this module. It's great to have people learning about waste, how to manage it, and the latest technologies to convert it into valuable products. This module is divided into 6 videos, where we'll talk about solid waste management and practices, current technologies to convert waste, and the latest global advances in solid waste technologies and policies. In this video, you will rethink waste, its meaning, its history, and its key role in addressing today's environmental problems. Our society produces a lot of waste. It is estimated that we produce over 2 billion tons per year of waste. This amount is equivalent to 200,000 Eiffel Towers. This value is expected to grow by 70% by 2050. Without substantial improvements, solid waste-related emissions are expected to reach 2.6 billion tons of CO2 equivalent by 2050. To give you an idea, we would need to plant and grow over 40 billion trees for a decade just to offset that much carbon. But what counts as waste? And why is dealing with waste such a big problem around the world? Let's briefly break down the history of waste. In prehistoric times, waste was mostly organic, biodegradable, and generated in small quantities. As populations grew, ancient civilizations introduced basic waste systems, such as street cleaning, drains, and dedicated dumping areas. But everything was mixed, with no separation or sorting of waste. The Industrial Revolution triggered an explosion in waste. Mass production flooded cities with hazardous industrial residues, overwhelming open dumping, and causes serious environmental and public health risks. In the 19th and 20th centuries, more advanced systems appeared: incineration to reduce waste, volume and produce heat and power, engineered landfills to contain pollution, and sewage treatment plants to clean wastewater before it reached rivers. These advances also created waste distancing. We throw something in the bin and it's gone. Waste is distanced, moved somewhere else, or handled by someone else. As society kept developing, more complex products were created, such as high-performance polymers specifically designed for electronics due to the rise in demands in aerospace, computing, and telecommunications. This increased the waste problem. And this journey led us to today, an era where waste dominates, often called the Wastocene. What we discard now shapes landscapes, societies, and create deep inequalities. These problems affect some regions a lot more than others. For example, e-waste dumping in West Africa or toxic waste sites near marginalized communities. Waste is usually defined in legal frameworks as any material or object that is discarded or must be required by law to discard. However, this overlooks several aspects that are context dependent. What is waste in one country can be a commodity in another. For example, spent coffee grounds in Europe are treated as waste, but they are sold as livestock feed in Vietnam. So waste is not a thing, it's a decision. A material becomes waste through social processes and value judgments. The same material can be garbage or gold depending on who looks at it. So there are different types of waste: municipal solid waste, industrial waste, hazardous waste, waste electrical and electronic equipment, biomass, and plastic waste. From all these waste streams, 2 fractions are especially important for solid waste management: biomass and plastics. For example, in municipal solid waste, we find biomass, like food, scraps, paper, and garden waste typically mixed with plastics from packaging and everyday products. In waste electrical and electronic equipment, there is no biomass, but there are many plastics in casing, cables, and connectors. And this is why the main types of waste we will talk about in this course are plastics and biomass. So how do we deal with these kinds of waste today? That's where solid waste management comes in. Solid waste management is the system that organizes how waste is collected, treated, recycled, and disposed. This is to protect health, save resources, and keep cities cleaner and more resilient. But reducing or achieving zero waste requires more than managing bins better. It also requires system transformation, and we have various frameworks to do so. For example, the zero waste hierarchy, which include 7 different strategies such as rethink, redesign, change systems, and redesign products so waste isn't created. Use fewer and safer materials and avoid overconsumption. Repair, refurbish, remanufacture, and repurpose so products keep their value and function as long as possible. Recycle high-quality materials and separate organics for composting or anaerobic digestion, ideally from nearby sources. Recover remaining materials from mixed waste, not for fuel, for example, sorting or advanced recycling. Stabilize and safely contain the small fraction that still remains in waste while using the data to improve systems upstream. Unacceptable, incineration, and other destructive and high environmental impact technologies or practices that depend on continuous waste generation. Another very well-known framework in waste management is the 4 Rs, which contain some of the components of the zero waste hierarchy, such as refuse, reduce, reuse, and recycle. Nonetheless, even with modern frameworks and advanced recycling technologies, our economy is still largely linear. We keep extracting, producing, consuming, and discarding materials, with landfilling and incineration still playing a major role, leading to air and water pollution, higher greenhouse gas emissions, and missed opportunities to recover valuable materials. Moving from linear to circular needs good waste management and technologies that recover resources instead of losing them as waste. For example, anaerobic digestion to valorize organic waste, thermochemical conversion to valorize waste into biofuels, chemicals, and biomaterials, or mechanical and chemical recycling facilities to convert waste plastics into new building blocks. Together, they keep carbon and resources in the loop much longer. Despite major progress, big challenges still block waste valorization technologies from becoming mainstream reality. For example, mixed, contaminated, and fluctuating waste streams make collection, sorting, and consistent operation of waste valorization plants difficult. Waste valorization plants need high capital, stable policy, and long-term contracts. Lack of incentives, permits, complex regulations, and local concerns can slow or block new facilities. And lastly, circular technologies must be fitted into existing waste, energy, and industrial infrastructure, which were designed for a linear model.